Welcome to the video lecture about Fourier Transform. In this video, we can understand its purpose and a small MATLAB code to understand the visualization and analysis of Fourier Transform. First of all, what is Fourier Transform? It is used to convert a signal in time domain to frequency domain. Time domain example is x of t is equal to sine 2 pi ft. This is time domain representation where amplitude with respect to time is represented. In frequency domain, amplitude will be represented in terms of frequency. Both the domains are very important. It has its own applications. Signal generation, waveform analysis, etc. we do using the time domain. The same thing for filtering, noise removal, compression, etc. We have to surely move on to frequency domain. So, to design a system, a signal processing system, we have to have both the time domain and frequency domain. So these transforms, Fourier transform, discrete Fourier transform, fast Fourier transform, everything are the mathematical tools that helps to conversion from one domain to another domain. Why use Fourier transform? First and foremost is frequency analysis. If you're having a signal with you, we have to identify what are the frequency component available in the signal. Always, we cannot say that a single frequency component is there. Along with the actual frequency that is to be transmitted or that is to be processed, unwanted noise signals will be also available. So, we can analyze that using frequency analysis. For that, the Fourier transform is needed. After analyzing whether the unwanted frequencies are present or not, we go for filtering. That's where it is used. In noise filtering, also, Fourier transform is used. In certain applications, we use only the high frequency component. In compression, what we do is we eliminate the unwanted low energy frequency component. So there also it is used. And again, in system analysis, we use Fourier transform. How the system behaves at different frequency. If you are designing a system that will work from 0 hertz to 1 kilohertz, how it works at 1 kilohertz, how it works at 2 kilohertz, or how it works at zero point 0.5 kilohertz. All those analysis will be done while we are going for engineering applications. So there also Fourier transform is used. In cases of feature extraction also we use Fourier transform. So Fourier transform is nothing but a mathematical tool which works with the formula x of k is equal to 0 n minus 1 x of n e power minus j 2 pi k n by n. K is equal to 0 to n minus 1. So this is the mathematical formula. So using this formula also itself we can understand it is for finite sequence because summation of 0 to n minus 1. N is some finite value which represents the sample size, sample length. And x of n is the amplitude at each instant. N we always represent the sample. It always here it is from 0 to 3. In the example 4 point DFT, you can see n is from 0 to 3 and corresponding x of 0 values also shown. For equivalent frequency representation, we use k. Here it is 0 to 3, x of k 0 to 3. So we can obtain magnitude spectrum and phase spectrum from this Fourier transform as shown. For an even and real signal, the magnitude will be symmetric in nature, whereas phase is asymmetric. So when you come to the computation for doing this mathematical operation on a signal, n squared complex multiplications are used by DFT. So there is an advanced Fourier transform, there is fast Fourier transform where the computation is in the order of n log n. So here the number of computations gets reduced in fast Fourier transform. So why computation? Because while going for hardware implementation, number of multiplication directly have an impact on the hardware structure. More multiplication, more hardware. More hardware, again, we have structural parameters which has to be taken care while we are going for a design. So those parameters will be affected if the computational complexity is more. So while designing itself, we look into all these things. Key properties of discrete Fourier transform: periodicity, which means that after certain n samples, the signal is going to repeat the same sequence. Linearity here, two signals are considered, x1 of n and x2 of n discrete sequence are considered. When x1 is multiplied by constant a and when x2 is multiplied by constant b and it is added in time domain, it will be similar in frequency also. Time shifting, the shifting of signals at n naught samples, what happens in the Fourier frequency domain is e power minus j 2 pi kn, k along with that n naught, that shifted time duration will be multiplied. Frequency shifting, it is like a reverse of time shifting. Conjugate symmetry is also possible in DFT. See, the applications of DFT are enormous. I listed only few, like signal processing, image processing, communication systems, audio processing, speech processing, biomedical signal analysis, vibration and fault diagnosis. This is in machinery fault detection. Also, we use it. So it helps us to understand the frequency content of a discrete signal, which is very, very essential in various engineering and scientific application. Apart from the previous application, it is used in medical imaging like MRI, CT scan, music processing, power system harmonic analysis. In finance and data analytics, also the Fourier transform is all used. Now, Fourier transform in more clearly, I have taken a MATLAB code where the sampling frequency is 1000, which means that every 1 millisecond the signal is captured and its discrete value is stored. This is the input sine signal that is generated using the formula x is equal to a into sine 2 pi ft. A is 1, amplitude is 1, it is given here. The signal frequency is 50 hertz. So f is equal to 50. Sampling is 1000, means every 1 millisecond the sequence is captured. See, this is 0. This is 0.001 x-axis. So that is n value, 1 milliseconds it is captured, and that at that particular time x of n is 0.309017. So this is how the sampling happens for a complete signal. Now, performing DFT. What we have done is we have used DFT for samples taken here. We have used this formula x of k to find the 6 of k, 0 to n minus 1, x of n e power minus j 2 pi n kn. So this formula is used in MATLAB coding, you can see here. Since it is summation, it is given in for loop, and using this DFT formula, the frequency spectrum is calculated, and you can see the 50 hertz at the amplitude 1, we have a single spike. For example, if I have generated another sine signal with 100 hertz frequency, and if its amplitude is zero point 0.5, for example, consider that I have generated, then we will get another frequency spectrum zero point 0.5 at the 100 hertz. If another signal is there, we can get the spectrum. So this is how the DFT helps to understand what are all frequency components that are available in the signal. Thank you for exploring the Fourier transform with us. Stay tuned.